Over 1,000 satellites are orbiting our planet, providing pictures and information faster and with great precision than ever before. Without satellites, life in our modern world would be unimaginable. Satellites come in many shapes and sizes and each orbit Earth at different heights, different speeds, and along different paths. Different planets of our solar system have dissimilar number of satellites. The first man-made satellite was launched by the Russians in 1957, called Sputnik, and it lost 22 days before the batteries ran out. It fell to Earth 3 months later. The Americans, not to be outdone, went ahead and created the first communication satellite, called Project Score. Amazingly, the satellite had 4 tape recorders in it and they could be controlled from the ground to record and play back messages. Since then, satellite technology has continued to develop from a tape recorder in the sky in advance to become a reflector, so the live signals could be sent and received. And shortly after that, satellites were created with solar panels to provide electricity. They could now pick up and repeat a signal so that it will be nice and clear. Satellite business began to boom and it solved all sorts of military and non-military communications problems. There are 2 types of satellite that orbiting the Earth, which is geostationary satellite and non-geostationary satellite. This is what our planet looks like from a geostationary satellite. This satellite is parked 36,000 kilometers above the Indian Ocean. Satellites orbiting at this altitude have an orbital period of 24 hours, so the satellite revolves around the Earth at the same period as the Earth's rotation. Geostationary satellite has several advantages, as it can be used as communication satellites and for weather-based applications. However, geostationary satellites have an Achilles heel. No matter which spot in the geostationary orbit we plant ourselves, we will still orbiting above the equator. From where we are, the high latitude regions are always hidden behind the curvature of the Earth. A geostationary satellite can never provide coverage for the polar regions. Apart from that, the rapidly increases use of non-geostationary satellite orbits such as medium Earth orbit (MEO) and low Earth orbit (LEO) represents an important innovation in satellite technology. The orbital period of this satellite can be more or less than 24 hours, and the directions of rotation is different as the Earth. Look, we are now orbiting the low Earth orbit. It takes only 90 minutes to go around the world. The satellite at MEO operating at altitude of 8,000 kilometers above the Earth, while at LEO it operating at altitude of 400 kilometers above the Earth. Being at a low altitude has several advantages. It takes less rocket fuel to bring us up. Being close to the surface, we can provide high-resolution images of the Earth, which is good for surveillance applications. For communication applications, we have the advantage of clearer antenna signals and shorter delay time for seeing the transmissions. Unlike a geostationary satellite, we are not confined at an equatorial orbit, so we can orbit with an inclination to the equator to bring us to high latitude regions. In fact, if we choose an angle of inclinations of 90 degrees, we get the polar orbit, which allows us to pass directly over the north and south poles. The one inconvenience about non-geostationary satellite is that a LEO satellite cannot provide coverage of any location continuously. Even when it passes directly over locations, thanks to its low altitude, it maintains line of sight with the locations for 10 minutes or so only. Because of the Earth's rotations, the next time the satellite passes directly over the same location may be after days later. Let's now talk about universal law of gravitation. Every object in the universe attracts every other object with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. With this data, we can write it mathematically like this. So, if the mass of any of the objects increases, the gravitational force will increase too. And more the distance between two objects, the lesser will the gravitational force. Directly proportional to the product of the masses and inversely proportional to the square of distance between them. This can be written as F equals to G times m1 times m2 over d squared. G here is called universal gravitational constant. As for centripetal force, it is the force that needed to stay in a circular motion. Like any force, it's going to be a mass times an acceleration. In this case, since it is a centripetal force, it's a mass times a centripetal acceleration. We know that for centripetal acceleration, it is equals to v squared over r. So that means centripetal force is mv squared over r. So the equation tells us that the force is equal to the mass times velocity squared over radius. Let's now move on to Kepler's law. Johannes Kepler published 3 laws of planetary motion, the first 2 in 1609 and the third in 1619. First law: all planets move in elliptical orbits with the Sun at one focus, and it is known as law of orbits. Kepler's second law: a line that connects a planet to the Sun sweeps out equal areas in equal time. The planet's speed will be slowest when it is far from the Sun, and it will be faster when it is close to the Sun. Kepler's third law says that the square of the orbital period of any planet is directly proportional to the cube of the radius of its orbit. A planet which orbits with a larger radius has a large orbital period. Okay, basically this is my satellite model. So this satellite model have power source, which is a solar panels to convert sunlight into energy, container to withstand the harsh environment, communication device to communicate with the earth, and lastly inside the satellite will have the fuel tanks, batteries and onboard processor.